So this would be my competency evidence for 2.3, which is this simplification of a distributed load. So in this question, we're asked to find the magnitude and location of our resultant force. And here's our picture. So we just have a beam coming out of a wall or mountain or something, a cliff, I don't know. But there's a trapezoidal force, so it's 100 foot-pounds up here and 50 foot-pounds down here. The beam is 9 feet long. So the first thing I did was, there are trapezoid equations, I just didn't really know them off the top of my head. And it made more sense to me to split it up anyway. And it made it simpler, I feel like. So I split it into a rectangle and a triangle and just solve for both of those, and I can add them together at the end, which we'll see. So I split them into this, and I just kind of colored that in so we can see it a little better. So there's our beam, and then we'll solve for the magnitude of that rectangle, the magnitude of the triangle, and then we'll add them together at the end. Because distributed load is essentially the area of a triangle. So to get the force acting on our beam, we do the height times the distance, and if you look at your units, you have pounds over feet for this, so that's the height of our rectangle, times feet. So our feet will cancel and we're left with pounds. So that is how you do a distributed load. That's how you get your force acting on your beam. So to start, I did the total force. So actually this calculation right here for my rectangle, and I just used a little rectangle because it sounded fun. So it'll be 50 pound feet times 9 feet gives me 450 pounds. So that's the distributed load acting across the entirety of the beam from just the rectangle. So now for the triangle, the area of a triangle is 1/2 times the area of a triangle, sorry, I was looking at the wrong one, is 1/2 the height times the distance. So it'd be 1/2 50 height times the distance of 9. That gives you 225 pounds. So that acts across the whole triangle. And then I did those, and then I found the distances, because we need to find the magnitude and the location of our resultant force. So I wanted to find the locations of my forces where they would act on our beam if I were to simplify it that way, which is the competency. So for a rectangle, I know that it acts right in the middle. That's how rectangles work. It'll be half of the distance. So for our x of our rectangle, we do 1/2 times the distance, 9 feet. So you get 4.5 feet, so that's acting right in the middle there. And triangles, you know that they act 1/3 of the distance from the high side. So that means our x for our triangle is 1/3 times 9 feet, so that's 3 feet. So that will be here, not here. That'll be 3 feet from the tallest side is where triangles act. So once we have those, we can find our resultant force and our location. So I did my resultant force first, so you just add them together, 450 plus 225, that gives you 675. So now we know the magnitude of our resultant force, but we don't know where it's acting because we've got a triangle, they're acting in 2 different spots. Our triangle's here, our rectangle's here. We gotta find where they act together. So to do that, took my resultant force, and I wanted the location of my resultant force. So I did x for the distance times my 675 for my resultant force acting on there, and I just added. So then that would be equal to the force and the distance of my rectangle and the force and the distance of my triangle. So 4.5 times 450 plus 3 times 225, and I put my units here just to show it because I like that. So it'd be pounds here for that one, and this would actually be in feet too, but we don't know that. If you didn't know your units, it would be feet times pounds plus feet times pounds. So then you'll get all those, you'll get that, you'll divide by 675 pounds. So your feet will cancel, so you'll have feet times pounds divided by pounds, your feet or your pounds cancel, you get feet, just to double check that I did it right, and you get your location of your resultant force acting at 4 feet. So we'll have a force at roughly here of 675 pounds, and it'll be 4 feet over. So that's how you simplify a distributed load to one magnitude and one location.